Since 2001, undergraduate mathematics students and future mathematics teachers at Brock University learn to design, program, and use interactive computer environments for the investigation of mathematical concepts, theorems, conjectures, or applications. The three project-based courses called Mathematics Integrated with Computers and Applications, or MICA for short, provide a different learning environment than most traditional university mathematics courses. In their weekly 2-hour lab sessions, students engage in programming-based mathematics projects aimed at a mathematics investigation or application. 2 weekly hours of lectures provide the mathematical context and background for their lab activities. The MICA 1 course introduces students to a 21st century way of doing mathematics, while it supports them to learn programming within a mathematical context. Topics covered have included prime numbers and hailstone sequences, RSA encryption, and discrete dynamical systems. In MICA 2 and 3 courses, students engage in increasingly more complex mathematical investigations and applications. Topics in these courses have been evolving from year to year and from instructor to instructor. For example, discrete and continuous dynamical systems such as predator-prey and battle simulations, cellular automata, and applications such as traffic flow, epidemics, stock market analysis, and so on. Students engage in increasingly more complex mathematical investigations and applications in MICA 2 and 3 courses. The courses are designed around individual projects, each ending with an original project for which students select their own topic. These projects count for a total of about 75 to 80% of student final grades.
Over the years, we've studied different aspects of the MICA courses, focusing, for example, on student learning, teaching, assessment, and course design, and others.
In this recent work, we were interested in examining the so-called constructionist character of the MICA courses, especially since they were not intentionally developed and adopted as such. So we examined the MICA implementation through the complete process of implementation. And that means separating the 3 stages that are design and adoption, classroom implementation, and student learning as an outcome. Our underlying research question was, how could constructionist mathematics courses at university level be described in order for a stakeholder to endorse and support its implementation?
In terms of classroom implementation, students in the MICA courses engage in mathematics by creating interactive computer environments for the investigation of mathematics, concepts, and applications, which can be connected to so-called microworlds. They are kind of using the father of constructionism, Seymour Papert's words, objects to think with.
So the goal of the third MICA project was to create a program that allows the user to input a cubic equation and then explore its dynamics. Coding the iterative process needed to achieve this goal forced me to really understand what was going on in class, because the concepts were no longer abstract, they needed to be applied to this concrete situation. After the coding was finished, we were asked to find some specific behavior where we didn't know what to expect. But having created a program designed to allow for exploration, I was able to use this and obtain some meaningful results and actually understand what was going on by experimenting with the program.
So MICA students are encouraged to reflexively engage in mathematics by making tangible mathematics constructions one of the principles defining constructionism. This is connected to creating shareable mathematics.
It wasn't just shown to the professor that was going to mark it, like we showed it to our friends and stuff.
Okay,
Yeah. I showed to my one friend that introduced me to the Sierpinski triangle in like 9th grade, and she thought it was pretty cool.
I showed it to my mother, just as I was working on it, just kind of get some feedback on it. And while she's not exactly really knowledgeable with baseball or coding or anything, she did provide some good feedback for me and like tell me about certain features I could add in or what she liked about it.
I have actually, because I volunteer at the spring open house and the fall preview days. I bring my project to show to all the prospective students, and as well, of course, I showed my family because I was super proud of it and really excited that I did something cool.
MICA students have the opportunity to engage in projects meaningful to them, in particular through their end-of-term projects in which they select their own topic. This engagement in something meaningful is another defining characteristic of constructionism.
We were looking at an environmental concern that was coming up in the real world today, and we were trying to find a unique solution or how other people can see what they're doing affects the forest in the long term. So this is a really applied project in the sense that we're taking the math we learn in class and we're applying it to an actual topic that we can see how you make a difference in the real world with it.
I'm a huge fan of baseball, if you can't tell already. Always been interested in it, and I just like getting into knowing why certain things happen, how certain things happen, so kind of really delves into the depths of what happens in a Major League Baseball game rather than just seeing like, oh, a guy got a hit, guy hit it to center field. It's why he hit it there and what factors led to that or what could potentially lead to him hitting it farther next time.
In this study, we did not examine the students' mathematics learning, that's part of another study, but rather we examined the students' views on the nature of the MICA courses. We did that through surveys. In the survey, we asked them, how would you describe the MICA courses to a student, a math student, from another institution? And their responses did support the constructionist nature of MICA courses.
You create programs that use concept and bring them to life to create a more concrete understanding of math and what it accomplishes.
This, for example, clearly highlights tangible mathematics as well as the reflective mathematics construction.
The courses teach you how to use an interactive programming environment and allows you to use it to investigate different mathematical theorems and concepts. It is very effective because it allows you to make your own program to be able to see how this concept works and play around with it to reach a further understanding of the concept.
In other words, the student talks about constructing objects to think with.
In 2000, the MICA courses were not being designed in the context of constructionism. We wondered what led to such a design. So we asked our colleague Bill Ralph, who played a central role in their development. We highlight some key ideas that we now associate with constructionism. For many years, Bill Ralph had volunteered and worked with mathematically talented school students from the Niagara region.
For years and years, they used to send me the troubled, gifted students from the local area to work with. And they would come in once or twice a week, and I would give them problems. Most of them tended to have a computational or a computer orientation, and I would give them tasks and things to explore. And so for years and years, I got into this pattern of trying to build wonderful, not problems is the wrong word, open-ended explorations for these really talented students to explore and see what they could do. And that was just amazing fun. The kinds of things that they brought were just extraordinary. And they've gone on to do amazing things. One of them is now a Google programmer, wonderful fellow. So I had that experience as well. So in two different contexts, so in Journey Through Calculus, I was building these explorations for students to learn calculus concepts. And then with the so-called gifted students in my office all the time, I was trying to create these open-ended explorations for them to play with and find interesting things. So I had both of those backgrounds going into the creation of MICA, and I certainly wanted a part of that to be in MICA.
Ralph looked for creative projects for the students to investigate, projects which were of interest to them. Ralph mentioned that many of those gifted students had a programming background and became completely immersed in their learning when they programmed an exploration of a mathematical concept or an application. He was pleasantly surprised by their engagement and enthusiasm, and also by the amount of time they were willing to devote to their task. In developing the MICA courses, Ralph commented that he aimed at recreating the individual experience of his gifted students in a mathematics class, including the vision that each student could claim, "I did something related to me."
The other thing from the humanities was, and that really did seem to be missing in mathematics teaching, was the opportunity to be creative. Students never, I think one of the most important things in teaching is that students see a reflection of themselves in their work.
Bill Ralph's vision led to a proposal of new courses called MICA, which were adopted by the Department of Mathematics as core courses in 2000. We examined the official departmental documents to identify the dominant elements defining the MICA courses, which describe the intended implementation and considered whether these elements were implicitly reaching out to constructionism. We did this to address our research question, namely, how could constructionist mathematics courses at the university level be described in order for stakeholders to endorse and support its implementation? Our analysis led to 3 dominant elements for an adoptable description.
A first element concerns the what, namely students learning to do mathematics by programming and then conducting their own mathematical exploration. In the official MICA 2 documents, one can read, students will be expected to do at least 2 major programming-based math projects that demonstrate creative application of the course content.
A second element concerns the why, namely, an explicit aim at empowering students articulated in pragmatic ways. For example, one can read in the official documents describing MICA 1, a goal is to help students build a portfolio of techniques which they are confident in applying to a diverse range of mathematical problems. Finally, a third element concerns the how, namely an implicit acknowledgement of constructionist student learning. For example, through the explicit role of the instructor in fostering and valuing student creativity in mathematical work. In the teaching philosophy section, one can read, to encourage creativity, the 3 MICA courses will challenge students.